Hello, this video will be about the Nobel Prize in Physics from 1914, awarded to Max von Laue for his discovery of the diffraction of X-rays by crystals, an important step in the development of X-ray spectroscopy. You see a crystal, these are the atoms, and you can see a beam of X-rays falling on the crystal, and you can see that this distance is of course longer than the distance this has to travel, and that distance, if the beam is aimed right, is a number of times the wavelength of the X-ray. As you can see, n is an integer times the wavelength is 2d times sinus phi, and this is phi, and this is also phi, and this distance is equal to d times the sinus of phi, and 2 times 1 time 2 times. Okay, the speed read first and then the Nobel Prize lecture. Shedding light on X-rays. The 1940 Nobel Prize for Physics issued two issues of identity that had perplexed physicists in the early 1900s. One was understanding the true nature of the mysterious X-rays, the other was how to prove the theory that crystals consist of atoms arranged in a regular lattice structure. At the time, there was a heated debate as whether X-rays are highly energetic particles or waves of electromagnetic radiation like light. X-rays appear to behave like light waves in some senses, but not others. For instance, when X-rays pass through a series of slits, they didn't appear to behave as light does when it resembles water ripples dispersing through reeds, a process called diffraction and interference. During a conversation with a colleague about whether shining light through crystals could help to reveal the structure, the connection suddenly struck von Laue. If, as was known, diffraction typically occurs when the distance between slits is of a similar size to the wavelength of light. The proposed size of spacing between the layers of atoms in a crystal lattice would be much smaller than the wavelength of visible light, and if, as some physicists had claimed, X-ray had a much shorter wavelength than light, then the spaces between the atoms in a crystal must be the right size to diffract X-rays. But an experiment based on an improbable set of assumptions produced a successful outcome. A beam of X-rays passing through a crystal formed a characteristic interference pattern of bright spots on a photographic plate. Laue's ingenious discovery of the diffraction of X-ray in crystals revealed that both X-rays are a form of electromagnetic wave and that crystals are lattice-like in structure. His work proved the spark for using X-rays and crystals to uncover the secrets of chemical compounds at the atomic level. As you can see, this is coming from the official Nobel Prize site and written by Joachim Pietz. You see essentially more or less the same illustration as we saw earlier. Yeah? Okay, then we go to the Nobel Prize lecture by von Laue himself concerning the detection of X-ray interferences. I have long been aware of the problem of producing I have long been aware of the problem of producing X-ray interference. Suddenly, if I, of course, von Laue, perceived the shortest path to success. I shall here explain the combination of scientific and personal circumstances from which the idea first arose. Röntgen had already tried to locate diffraction and interference phenomena. This so whether they represent a wave or a particle phenomenon. They should solve. This research met with failure. Stokes and Weiger supported the wave opinion. According to Maxwell-Lorentz electrodynamics, electromagnetic waves must be produced whenever electricity carriers alter their velocity. One was also aware that the cathode rays, which induce X-rays on striking an obstacle, are made up of electrons. Wien tried to reconcile with the very young quantum theory and came up with an estimation for the wavelengths between 10 to the minus 10th and 10 to the minus 9th centimeter. The strong penetrating power also pointed to a short wavelength for X-rays. An experiment for diffraction or interference for X-rays had thus have much smaller dimensions compared to that for visible light. Haga and Wind and Walter and Pogue used wedge-shaped pointed slits. A broadening of the beam was seen attributed to diffraction. Koch repeated the result, measuring a wavelength of 4 times 10 to the minus 9 power centimeter, which Sommerfeld accepted as proof of diffraction. Barkas gave further evidence for supporting the wave theory. He proved that X-ray can be polarized. This can be explained by particle theory only with extreme difficulty, but it's much more easy to do with wave theory by transversal oscillations. The wave theory was still not completely accepted. Bragg pointed at several phenomena that are not explained by wave theory. If X-rays fall on a body, they do not only create secondary X-rays but also free electrons. The velocity of these electrons do not depend on the temperature of the body. The energy must come from the X-rays, but the velocity does not depend on the intensity but on the hardness of the X-rays. The intensity of the rays only influences the number of the electrons released. It would be understandable if the energy of the X-rays would accumulate and remain at certain points like a particle, but the energy spread as a wave over increasing areas. The same happens with short-wave visible and ultraviolet light rays in the photoelectric effect. Einstein connected the velocity of the electron with the frequency of light wave, with the size of rho over h, Planck's constant, the elementary quantum of action. Wagner shown that by the reverse process, the excitation of X-rays by cathode rays, the same constant appears. Here we have the great quantum mystery, a new field of physics. The situation before 1912. As a student, I was particularly interested in the theory of light and also a special feeling or intuition for wave processes. My first independent work was on the propagation of natural radiation, dispersing substances, thermodynamics of interference phenomena, etc. I was obliged to seek mathematical representation of the lattice theory applicable to lattice grids and even to space lattices. In 1909, my attention was drawn to the work of Röntgen and by Sommerfeld's interest in X-rays. Apart from that, the crystallographic law of rational indices, Hoe and Bravis, had been explained through the space-lattice arrangement of the atoms. Sohnke, Fedorov and Schoenflies brought this theory to perfection. This was not very well known by physicists, but it was in Munich, and via Groth I learned about it. Ewald visited me in 1913. He did mathematical work on long electromagnetic waves in the space lattice. Later he published a dissertation on the theory of crystal optics. Ewald came to me for help, but in fact it helped van Laue. It became clear that the lattice constant in the crystals is in the order of 10 to the minus 8 power centimeter. The order of the wavelengths of X-rays is in the order of 10 to the minus 9th power centimeter. This one might expect interference phenomena when X-rays are transmitted through crystals. Friedrich heard of it too and expressed his willingness to carry out a relevant test, but others doubted whether the whole idea. Diplomacy was needed to get Friedrich and Knipping permission to carry it out. Copper sulfate served as the crystal. The irradiation was led to chance. The photographic plate behind the crystal showed the presence of deflected rays. The lattice spectra we were expecting to see in figure N. We will see it shortly. Friedrich and Knipping then, with more equipment, continued with irradiation in the crystallographically indicated axial direction of crystals of maximum possible symmetry. Sommerfeld was able to present the work on X-ray interferences. See figures 2 and 3 a little later. We'll show them. Each point of the interference corresponds with 3 integral numbers originating from the 3 space lattice periodicities, the ratios which determine its position. The attribution of these numbers was done in a second publication. The Braggs have reckoned the numbers and found them to be accurate. This benefited the wave theory of X-rays, but also the lattice theory of crystals. The wavelength can be determined from the 3 specified numbers. I could not attribute to the values of the wavelengths the same reliability as to the ratios of the numbers. In its maximum, one has a wavelength, but it's also its half, a third, etc. This is known in optics, therefore the wavelengths remain uncertain. The wavelengths were measured by the dimensions of the space lattice. For high accuracy, one would have to know the molecular structure of the crystal to the last decay. Other lattice forms than space lattices also do exist. The Prax did that gave exact wavelengths. The changes to the theory have been minimum, only on the density a new factor was added. Many others followed the set example. Interference of X-rays was soon accepted. Also thanks to the work by Wagner and Glocker. The crystals were examined, the space lattices. The crystals were also used in spectroscopy. The Braggs led in both types of experiments. De Beyer constructed an experiment with well-formed crystal fragments, crystal powder. Mosse, Manne-Ziegbahn and Zennström determined the characteristic spectra of the great majority of the chemical element. It contributes to the knowledge of the structure of the atom. The question why the thermal motion of atom does not disturb the interference phenomena has been settled by de Beyer. Lorentz showed the manner in which the interference points which originate from the continuous spectrum obtain their energy from the energy of many neighboring wavelengths. One open question on mixed crystals. Are there, for instance, potassium chloride and rubium atoms distributed over the reserved spaces for atoms or randomly or regularly? Von Laue prefers the latter, but that is not proof. Irritation tests by Vega and Scalyup seem to favor the first view, but for Tamman's test, the opposite is true. This is a new field of endeavor for X-ray interference research. Well, this was a summary of the lecture by Van Laue. If you want to read the complete lecture, you can follow the link, of course. And here you see the 3 figures that were named in the text. Yeah. And here are some figures coming from an original article by Van Laue on X-ray experiments, as you can see. Originally written in German, as you can also possibly see. Okay, this was it for today. Next week we will do 1915. Maybe till then. Bye.